Hello? Yeah. So I hope you can, all of you can see the PDF page. Ma'am, can you please respond?
Yes, we can see Urvish.
Yes.
Okay. Okay. Thanks a lot. Okay, let me make it full screen so that. Okay, cool. So I think it is now in full view. Okay, thanks a lot. So before proceeding, let me just kick this talk off by starting a prayer. Um, my prayer to my Gurudevs who actually taught these beautiful algorithms to me, and to Mata Sharada, who's always been there helpful in my educational endeavors. I pray at the benevolent feet of my all Gurus. Shri Gurubhyo Namaha. Shri Shardambikaye Namaha. Harihi Om. Okay, yeah. So first of all, thanks a lot for giving me this opportunity to present this talk, which I actually started deciding, okay, that I want to talk about this because after inventing the algorithm which ma'am actually told about, which is fast approximate floating point arithmetic. So it was only after that that I started inquisitively looking after how actually computer arithmetic works. Previously, before that, I had a brief overview of, okay, this is how it would work. But then after getting a deep insight, I thought of, okay, let's just share it with among our fellow students as well. Okay, so that is my major motivation here. I hope you like that talk because I'll try covering it for, all the basic aspects as well as the advanced concepts as well. Okay, so this is one of my, I think this is the 26th lecture which I have conducted online. Okay, so I do enjoy lecturing quite a lot. So when I was in Pune during my bachelor's, I enjoyed taking talks on the subject which I researched upon. So be it fractional calculus, number theory, or electronics. This is how I started gaining interest. So this is a known Feynman technique that I even advise other students to do that. So let's say if you are quite good at something, don't only keep it to yourself, but start distributing it with your other fellow friends and students as well. Okay, so not only limited to your college, but try making friends at other colleges. So you'll end up making a ton of friends, and even that will help exploring your network. Okay, so let's go ahead. So today's aims and objective is, so what my aims and objective for this talk are, and then I'll give you a set of motivations so that, okay, you'll find that, okay, only after seeing those, I think you'll be motivated to learn more about this topic. Okay, so I cover a set of 4 major motivations. So one of them is quite recent, which is the Y2K22 bug. Okay, this was introduced at the starting of the new year. Okay, many software companies like Microsoft, even Xilinx was affected by it. And they say that even electric car companies like Tesla and even Honda was quite affected by this bug. So just a software bug, nothing to worry about. People have already bypassed this with a very intelligent algorithm or a trick, I would call. And then I'll discuss a very expensive bug, which is the ARN5 crash. So which, I mean, it was only after investing such a huge amount that people thought that, okay, this was, the people then discovered that, okay, this simple rounding technique was actually a bug. And then next is the Intel Pentium floating point division bug. And then lastly, which is what all students face, which is the crazy competitive programming. Okay, I think many people are missing out on the computer arithmetic fun, which they could explore by studying competitive programming in a proper light. Okay, and then I'll also provide you some hands-on approach with the nitty-gritty details, what actually floating point standard is, and how are what are the different techniques of going about doing computer arithmetic. So how does computer in hardware do the arithmetic? And then lastly, there is all play. So I like to keep it all play. So for me, there is no work at all. So I actually feel very guilty that for my organization that they pay me salary for having fun. Okay. Okay. So jokes apart. So I'll discuss a few fun applications, which is actually an algorithm which is quite funny and very deeply influential for me, at least. And then lastly, I'll give you some interesting reads such that that will help you cure your own needs for learning this topic. Okay, so starting quickly. So my first aim and objective for this talk is to make attendees conscious about floating point data type and the compute overhead associated with it. So after this talk, if you start using, or if you go about programming something, and if you randomly use float x equal to something, I want you to feel conscious that, okay, this is how it will get implemented in the computer. And you'll have a sense of understanding that, okay, this is the target application for me to realize, and these are the data types which I can use or exploit for that particular thing. Okay, just because it has been classically been people are doing it that way does not mean you need to do it that way. Okay, and then the second thing is that I will motivate you to understand the mathematics behind that float data type or even integer data type. And then the third, which is the most important point, is I'll help you understand, or such that you will be able to exploit the floating point format with formal mathematical reasoning. And as I already told, I'll try to give you enough motivation so that you can curiously look for improvement for these custom or hybrid or arbitrary precision floating point data types. Okay, so one good thing, just a general higher order view for what I'll be discussing is, you need to understand that mathematics is a tool to meditate rather just to compute. So this is a quote which I adopted from the book Fooled by Randomness by Nassim Nicholas Taleb. Okay, it's quite an interesting book. I suggest you everyone to read it. It is just off the topic, but quite well written book. And there's also a quote which says that the aim of computation is insight. Okay, quite some deep quote, but I hope you'll be able to correlate today's talk with these quotes. Okay, moving ahead. So what happened at the starting of New Year is many companies like Microsoft, Xilinx, and even Mitsubishi and even Toshiba, they started seeing this bug, okay, which was named as Y2K22 bug. Okay, it is just because it was unfolded in the year 2022. Okay, so what happens here is that if you see, okay, so this simple bug, it caused a lot of error, be it exchange mail servers or even in big softwares. Okay, so it started crashing after just on the first day of 2022, and then this troubled quite a lot of software engineers. Okay, now what happens there? Let us start. Okay, so if you see timestamp, okay, there's a concept called timestamp, which is actually associated with that particular software and is given in this format. If you see, it is YYMMDD and then hour and minute format. Okay, so when on the starting day of New Year, this timestamp was something like this. Okay, because a number which was used to store this timestamp was nothing but a 32-bit integer. It got tripped off. It started rounding, because if you see this number which is there, 2201010001, is higher than the number which a 32-bit integer can accommodate. So as a result, it started tripping off, and then it started giving erroneous dates. Okay, now how did the folks fixed it? Okay, so I just started taking a look at some Reddit channels, and surprisingly, I find that they tried to fix it with a very intelligent fix. Is that now they don't save the date year format as 22, but rather they keep it 21 only. But interestingly, they try incrementing the date. Okay, so rather than it is the actual date which it stores is nothing but December 33rd of 2021. Okay. Right. So you can try going about, you can try search about this problem. It's quite fun to read and understand this. Okay. Yeah. So moving ahead. So the Air 5 crash. So what happened here is that if you see there's this images or very vividly taken images of the rocket called Air 5. Okay. So what happened was it took 10 years for European Space Agency to make this rocket and a price of almost $7 billion. Okay. And there's only one small bug inside that, which actually pulled the toss upside down. Okay, so what was that? Is that it seems that the horizontal velocity component, which was getting stored as a 64-bit floating point number, it was rounded to a 16-bit integer integer space. Okay, so imagine 64-bit. You're rounding even if you round a 64-bit integer number to a 16-bit integer, there's a huge loss of precision. Imagine rounding a 64-bit floating point number so that floating point are classically known to store huge value of numbers, while integer store a limited value of numbers. So that actually tripped this entire software which was there inside this rocket, and that resulted in an explosion of this entire setup. Okay, so far so good. So this was actually this event was covered in a news coverage by New York Times by their reporter called James Gleick. It's quite an interesting and detailed report. I have embedded the source to understand more about this. You can take a look. At the end, I share a link for this PPT as well. You can happily take a look at it at your own leisure time. Okay, so one more quick comment about this is I was trying to discuss this on LinkedIn with some of my colleagues. Okay, so turns out that people jokingly remarked about this, that it's like taking all the passengers, almost just keeping the 2 passengers in the train while removing the rest and then throwing them down on the rail track. Okay, that was the thing. So it is, you can approximate that event using that analogy. Okay, next thing. So it is the next bug, which is the Intel Pentium floating point division bug. Okay, so Intel started manufacturing these Pentium chips, and turns out that there was a small error in the lookup table, which was actually used for computing a division value. Okay, so that error caused this particular division here to give a erroneous value this. Okay, so the digits in red are erroneous digits. It should have been something like this, which is given at the very right of this slide. Okay, so interestingly, if you see, I tried understanding, or interestingly, it was discovered by a professor who was trying to enumerate primes using computer. Okay, so go back to your first year engineering exercises, which is you write a computer program to find whether a number is prime or not. Right, the vague way of going about doing that is to compute, to try to divide, use the Euclid's algorithm, which is try to divide that particular number with all the possible numbers less than or equal to square root of n, right? Where n is the number you are trying to test whether it is prime or not. Okay, so here Professor Nicely, that was his name. He discovered that bug in the year 1994. Okay, when he was trying to enumerate primes and even dual primes, twin primes on a computer. Okay, there was yet another professor on a related research note. His name was Professor Richard Crandall. Okay, he was such an eccentric professor that he started using Apple's Macintosh for testing primality of a particular number. Okay, so that number happened to be a very gigantic number, let's say 50 digits, 100 digits, and so on. So try thinking about that problem, and then you'll end up appreciating the work of Professor Richard Crandall. Okay, so And interestingly, there was another ton of events that happened, that this man who actually tried lecturing about his talks at the at the Reed University, where surprisingly Steve this fellow called Jobs, the CEO of um, Apple back then, he was present there for recruitment of people. Okay, and he attended this professor's lectures through the window of that class, and he found that okay, there was this some professor who is actually teaching computer on Macintosh, and what is he trying to teach? And turns out he ended up recruiting that professor for his company, and he went on to become the first chief cryptographer of Apple. Even today, 13 of major cryptography algorithms which are still there in iPhone are uh, are what to say are designed by Professor Richard Crandall. Okay, so okay, I would like to, and this book which he has written called Primes: A Computational Perspective. Okay, and even on a related note, so I just told you about Euclid's algorithm of finding the primality of a given number. But if you see, the compute complexity of that is approximately equal to square root of n, right? And the latest, if you try to see, the latest lowest complexity algorithm was offered by a trio of Indian guys. Okay, it's called AKS algorithm, Agarwal, Kayal, and Saxena. Okay, Professor Agarwal, he's the head of computer science and engineering department at IIT Kanpur, and two of his PhD students, Mr. Kayal and Saxena. Um, I believe I read somewhere, just I'm not sure about that, but seems like they completed their PhD by inventing this algorithm within 3 months. Okay, so that's quite interesting. I believe so. They have written, the authored this paper called Primes is in P. Okay, the title itself goes by that they have given a polynomial time algorithm to find whether, or to test the primality of a given number. Earlier it was called to be as NP problem, which is non-provable. Now they have shifted it in class P, which is provable. Hence their paper title starts as Primes is in P, which means Primes is in class provable. Okay. Okay. Next thing is, I don't want you to show this meme. Okay, I'll unfurl it later. So many of my competitive programming friends, okay, all of you who are here present, you might be using the float double data types just at your convenience. Okay, so be it any number, you just end up using this. Okay, this is something which is quite wrong, I feel. Okay, you need to understand that what data type should be assigned for that particular application. Okay, so they just I somehow I asked one of my good friends that why you just go about randomly choosing the double or float data type for your application, and he sent me this meme. Okay. Okay, so it kinds of sums up the attitude of people or the students who just, they have to do it in some time, and they have some finite time for doing that. They end up choosing the optimal values, or whatever the best possible values you have. Anyway, moving ahead, I want you to just take a note that henceforth, be it competitive programming, unless it is you're cracking an interview of a very renowned company, I want you to understand that what how to go about choosing the data types, which I'll discuss in the next slides. Okay. Okay, so first thing is, what necessitated the floating point standard? Okay, so let's start with the number concept itself. So let's say if you want to represent speed of light, how would you go about doing that? Right, by a naive way, or if you were a child, you would you say that okay, I'll write that 3 and then I'll append 8 zeros after that. Okay, that is how you'll do that. It is 3 into 10 raised to 8 meter per second. Okay, but is that a very clever way of representing numbers? Right? No, I don't think so. Because if you were to represent numbers just the way as they were, imagine writing Newton's gravitational constant, which is 6.67 into 10 raised to minus 11. Okay, you'll have to search for, you'll have to see each and every decimal places and then counting it. That would be very erroneous. Okay, so mathematicians, early mathematicians like Bhaskaracharya and even Bhaskaracharya the second, they tried to approximate or to give a very handy representation, which we now call it as scientific notation. They try to give a number, they try to round the mantissa and give the next powers of 10. Okay, so in early mathematicians, they called it as Shanku, Padma, Kharga, Visarga, and Mahapadma. These are nothing but the powers of 10, just like what we have today: nano, milli, kilo, mega, all the way up to the astronomical units, right? Okay, so okay, next point here to understand here is, so if I tell you what is the speed, if I ask you what is the speed of light, you quickly associate it with this tuple, which is 3 and 8. Correct. 3 is nothing but the mantissa and 8 is the power of 10. Correct. So when you have to regenerate that constant, you just take these two tuples and then place them in their respective positions. Similar way happens with Newton's gravitational constant as well. You don't remember that number as it is. So you just try to remember the mantissa and the power of 10. Okay. Now there's one more trick. So if you see closely, speed of light is not equal to 3 into 10 raised to 8. It is approximated by that number, but it is rather a very big number, which is 2.9979248. Okay, into 10 raised to 8. So why don't we store it in this format? Okay, in computers you can do that, of course, but imagine a number which is quite large, maybe pi 3.14162, and then it goes on, but you cannot quantize it using finite computers, right? So we have to approximate that. That is where you try to quantize, that is where you try to approximate the mantissa, and that is why we store it approximately as 3 into 10 raised to 8. So we have some finite precision bit width that is allocated to store the mantissa, and we have a finite precision bit or some storage which is allocated to store the exponent. Okay. Yeah. So that is how we store it, just like the scientific notation. That is the same way with the floating point standard. Okay, just the only thing is that notice that computers are working with binary numbers, because at the end they have transistors working as switches internally inside a processor. There are billions of transistors which actually work as switches, and they try to give you your desired output. Okay, so just remember that the number way we store just the way we do it for scientific notation, the same way it does it for floating point, but it is stored in binary format. Okay. Okay, so far so good. Now coming to the fixed point arithmetic. Now there are two arithmetics I told you. So one is fixed point and another is floating point. So floating point we just discussed. Now fixed point and floating point, if you see, the nomenclature itself gives you the idea of how the decimal or the binary point is. Okay, for a fixed point, the decimal point is fixed, but for a floating point, it is floating, not in the air, but in the representation. Okay, so it is floating. So why do we say it is floating? Because if you see the decimal point or whatever this mantissa is stored with some given format. So even in the scientific notation, it is limited to a number less than 10, if I'm not sure, if I'm not wrong. Okay. So this mantissa, if you were to store it as in scientific notation, the rules say that you should limit this number less than 10. Okay, and adjust this mantissa accordingly, or the exponent accordingly. Okay, similarly, we have some predefined mantissa width that is allocated to store floating point, and then the rest, or the mantissa of the floating point, and the rest is stored as an exponent. Okay, that is why the binary point keeps shifting here and there. That is why they termed it as floating point. Okay, nothing to worry about here. So fixed point, as you understand, it is fixed. That means if I were to say if I were to give you two fixed point numbers, it is as good as if I give you two fixed point numbers, and if I want you to perform some operations on that, it is as good as performing operations on simple arithmetic, which is which you have learned in your high school. As simple as that. Just keep on adding, multiplying, whatever, by hand. Okay, as simple as that. Okay, let me give you an example. See here, particularly if there's an fixed point, this binary point is not stored anywhere, but it is stored in the head of a programmer. Okay, is actually thinking that, okay, because it is fixed point, he assumes a particular scale. So says that if I give you a bunch of numbers and I say you, okay, they're all in fixed point. Okay, what I particularly mean is that they're all divided by 10 raised to something, maybe 10 raised to 2. Okay, or in this case, because it is in binary, I say that it is divided by 2 raised to 4. Okay, but you are free to do the addition, subtraction as assuming they are integers. That means you want to shift this decimal here. Okay, for your convention. And then at the end of calculation, you again say that, okay, oh no, the decimal point is here. As simple as that. Right, it is scaled up and then you do the calculation and then scale it down back again. Okay, so far so good. I hope the mathematics which I explained was clear. If not, feel free to interrupt me. I'll again explain you once again. Okay, now the thing is, now imagine you were to do fixed point arithmetic using computers. Now what happens here is, let us say if you want to perform addition of two 8-bit numbers, how many bit width would the resultant require is given by this equation. So bit width of the operand or the result, let's say if you wanted to add x1, x2 to binary numbers having the bit width of beta of x1, which is, let's say 8, it gives you 8, and even beta of x2, it gives you 8. Then what would be the resultant bit width of that particular result? So it would be given as max of this beta 1 comma beta 2 and then plus 1. So let's say if your input operands are 8-bit and 7-bit, then this max operation would give you 8-bit, right, and plus 1. So the input resultant should have 9 bits in order to faithfully store the output of your resultant. If you still limit it to 8 bits, what will happen is it will have problem storing the maximum value which will be there. So try doing it this way. Let's say if you have 4-bit number or even 2-bit number, what will be the maximum value of a 2-bit number? It is 3, right? 1 1 3. So if you say add 3 plus 3, it is 6, and minimum value or a minimum binary precision required to store 6 is 3, right? So 2 bits, if you add take max of 2 bits, 2 comma 2, it is 2 plus 1 3, right? You need a 3-bit number to store 6. That is what it means. So similarly for multiplication, what happens, so it's quite intuitive. So for addition, it is in this format. So for multiplication, it is in addition format. So if you were to multiply two n-bit numbers, the output should have n plus n bits, which is 2n bits, in order to faithfully store those numbers. Okay, so this is what these equations mean. Now you would ask me what about division and subtraction. So let me tackle subtraction first. So subtraction in binary is nothing but 2's complement addition, right? So if you remember that, this same rule applies here. Okay, but for division, it changes. So for division, I point you to this interesting resource, which is Fixed Point Arithmetic and Introduction, quite a detailed review paper by Randy Yates. So this was the guy who actually designed Motorola processors. So these days he hosts a website called Digital Signal Labs, quite an interesting website. Okay, people who are interested to study digital signal processing, I encourage you to visit this paper and his website in general. Okay, moving ahead. So this I already explained. Now floating point standard, coming back to floating point standard, what happens here is, okay, so just like we store speed of light, right? Which is 3 into 10 raised to 8. So similarly in computer, we have some precision attributed to store mantissa, some precision attributed to store exponent, and 1 bit to decide the sign, right? So this is how the floating point number is stored inside a computer. When they say that, okay, 64-bit precision computer is there, it means actually it has 64 bits of address and data precision bits, and it can handle these compute data paths. Even modern day compute architectures like GPU, they're inherently designed on these 64-bit precision floating point data path. Okay, so inside a GPU, if you see, it is doing the computation assuming that the number that is coming is floating point. Okay, so that is how it works. So GPUs are known to preserve very high accuracy. Okay, so mathematically it is represented in this format, which is x equal to minus 1 raised to s. Okay, when s is 0, sign is positive. When s is 1, it means that it's a negative number. And then 1 plus small m divided by 2 raised to capital M. What is the small m? Small m is nothing but the mantissa, or whatever number gets stored here is the decimal equivalent of that, divided by 2 raised to m. Okay, now why did I divide here, or why did they divide here by 2 raised to m? It is simple that it is stored as a fractional bit. So let's say if you have pi which you want to store, so it is 3.14. What I'll do is I'll discard that 3, I'll store it somewhere, but I want to store the rest of fractional part, which is 1.14. So that 0.14 is getting stored here. Okay, similarly, this 1 plus, so understand that this 1 is not getting stored anywhere. It is for the computer to understand. Okay, so by doing this intelligently, they also give you, or they double the dynamic range of this allotted mantissa bits. Okay, we'll come to that later. But understand that this is nothing but a mantissa bit, which is mantissa bit width, which is allocated to store the mantissa. And if you were to read it as a decimal number, you would get something as m, small m. Okay, I'll denote it by small m. And then multiplied by 2 raised to e minus b. Now e is the exponent in decimal. If you were to read the exponent bits in decimal, you would I denote it by small e, and minus b. And then this b is nothing but the bias, which is used to manipulate the signs of the exponent. Okay, so that's it here. And one more thing is, there are multiple different standards. Okay, so there are floating point 32, floating point 64, which is called the double, and there's this FP16 as well, floating point 16, which is the half precision. Okay, so softwares like MATLAB, Java, they inherently store their each and every variables as a double bit, or as a double precision floating point number, which is FP64. So for that, exponent bit happen to be 11 bits and mantissa bits are 52. Okay, and there is one sign bit, of course, that I've omitted just because for it's general, right? So it's easy to understand that there exists one sign bit. Okay, if you add this, you will see that it is 1 less than 64, which is 33. I mean 63, sorry. Okay, and similarly goes in for this as well. Okay, now you would ask me that how to actually decide whether which numbers are to be stored as a float and which to be stored as integer data types. So answer is simple. Okay, so first thing is understand that how are numbers generated in a computing system. Okay, so we actually try to quantize a real-time data and we want to store it. So the better your quantization, the better the result, right? The computational result. But in some cases like digital systems, right, which we have real-time digital systems like the communication system or this video system or whatever, Okay, these are real-time digital systems and they are quantized heavily. Okay, and for that, if you see how do we quantize the real-time data, is nothing but we use transducers. So transducers convert some physical quantity into, I mean, some physical equivalent into an electrical equivalent, right? So in similar fashion, we try to store it. So we try to quantize it using the analog to digital converters. And if you see, ADCs are typically, they are available in the range of max 16-bit, 18 bits. And there are even ADCs which are available in floating point standard as well. That means they take the analog data and then they quantize it in floating point standard, and then they give you, literally they give out 32 pins of these floating point bits. Okay, so but classically ADCs are limited to integer bit width. Now imagine that ADC or the data which is coming to the computer via ADC is itself is in integer. Then why would you need this floating point to store that? Right, you have to limit it in integer precision only. Okay, but in case of applications like scientific computing or medical image processing application wherein precision is very important, there you have to play around with high precision data. And even although it may be coming from ADC, we want to store the highest precision and we don't want to lose any precision bits, then you are happy and safe to use floating point standard. Okay, so even in scientific applications like astronomical image processing, or even some scientific number crunching, okay, those require floating point standards. Okay, next. So I think if you try to find the root cause of, okay, how to go about deciding which standard to use, I think it is all about dynamic range. Okay, so what is dynamic range? It is a measure of how many numbers can be represented using a particular standard. So let's say if you have 2-bit integer, okay, 2-bit numbers to be represented, then what are the possible values? 0 0 0 1 1 0 1 1 4, right? If you try to extrapolate it, you'll see that it is nothing but it is 2 raised to n, where n is the number of bits. Okay, similarly, so dynamic range is defined as ratio of maximum positive number that can be represented using that standard and ratio of minimum positive number that can be represented. Okay, so you can derive an expression and then you can see that, okay, for fixed point, any fixed point number, the dynamic range can be given as 2 raised to b minus 1 is approximately equal to that, where b is the number of bits you want to use. Okay, so for 32-bit fixed point, it is like this. It is 2 raised to 31, which is approximately equal to 2.14 into 10 raised to 9. Now, if you see this is where the fun begins. When you want to compute the dynamic range of floating point 32. Floating point 32 has a dynamic range of 2.909 into 10 raised to 76, such an astronomical number. And even dynamic range of 64-bit floating point number is 0.806 into 6 into 10 raised to 616. Imagine. Okay, so for reals, if you were to do some pen paper based arithmetic, in the real numbers or integers, theoretically the dynamic range is infinity. The better you approach the infinity, the better the resolution. Okay, Claude Shannon, the father of digital designs or the digital electronics, he remarked once beautifully. He said that information is resolution of uncertainty. Okay, the better you resolve a particular uncertainty, the better information you have. Okay, next. So moving to the data path implementation. So let's understand how it is getting implemented in computers. Okay, just allow me for a second. I want to take a sip of water. Okay. Okay. So Yes. So yes, coming back to the data path implementation. So data path implementation is a fancy word to how actually a compute path is implemented. So in computing system, there are um, two paths, which is a data path, which is actually responsible for doing compute, and then there is control path, which is orchestrating that compute. Okay, that okay, you come here, you go there, and that is how it is being designed. So if you see modern FPGA architectures, or they call it as SoCs, they are embedded with some fabric, FPGA fabric, which is generally used for this data path implementation. And then there sits the ARM processor, okay, which is serial in nature, unlike FPGA fabric, which is all parallel. Okay, so see, because it is just doing control logic, then why to go about wasting parallel, uh, parallel computing architecture style. So that is how they are implemented. Now let us understand that how the computer does that. Okay, first we'll tackle the multiplication. So in order to understand that, let's consider the famous mass energy equivalence given by Einstein, which is equal to mc square. Understand that, or let us assume that you have a mass of just 2 milligram or 2 gram. Okay, 2 gram, which is 2 into 10 raised to minus 3 kilogram if I were to convert it into SI units. And you multiply it with the square of speed of light, which is 3 into 10 raised to 8 meter per second, again in the SI unit. What I have here is this, again this mass times the speed, which I squared it easily. Okay, here. Now what you do is you try to multiply these two integers and then you try to add these powers, right? So after multiplication, what you have here is 18 and the addition of power fetches you 13. Okay, 16 minus 3 is 13. Okay, so it's easy. Just multiply the mantissa, add the exponents. Okay, easy. Now let us understand you if you were to do the addition. Now what happens here is this, assume that you have, for that I've demonstrated using Kirchhoff's law. So incoming current is equal to outgoing current. Okay, imagine there's this outgoing current 2 milliampere and there are two incoming current, which is 1 microampere and another is 1.999 milliampere. Okay, if I were to standardize, so if I want to add I3 and I2, I need to normalize their exponents first. Okay, convert them back all in milliampere and then I will add it in order to prove that Kirchhoff's law holds. Okay, so see what all compute overhead has been involved. I need to see, okay, what is the unit of this other operand. I need to normalize this 1 microampere in that respect and then I have to add them. Okay, so that has required a bit of compute. Okay, in hardware again, if you see the implementation is as discussed. They multiply the mantissa, add the exponents, and there is some logic to decide the sign of the resultant, and it is easy peasy stuff. But when it comes for addition, the data path is quite complicated. Okay, so what I want to show you here is understand that compute overhead required for floating point addition is greater than floating point multiplication. Okay, it's irony, but it's true. Okay, you can see it for yourself. In order to understand more about this, there's this interesting book by Karl Hamaker and Safwat Zaki. It's called Computer Organization. Okay, it's a very interesting book. I encourage at least the computer, the folks who have their majors as computers and electronics engineering to take a look at this. Okay, so it's a good reference. The book comes with a very abstract painting on the cover. Okay, don't be afraid of that. It almost looked like a digestive system track to me at the very first shot. But forget about that. The book itself, internally, it is quite dry. I would say there are no figures. The font, but the good part about that is that it is typesetted in LaTeX. Okay, the way I have typesetted this presentation. I'm a big fan of LaTeX. Okay, coming back to some major things. Okay, I have 10 minutes with me. I'll cover some things and then I'll have some two and I'll leave some time for question answers. Okay. So recent innovations. So seems like Elon Musk heated up a wave of discussing floating point arithmetic on Twitter. Can you imagine that? No, right? So this fellow is almost. I'm not a big fan of his either, but just I appreciate the fact that how multifaceted he is. Okay, he tries to do some very shiny stuff, and at the end of the day, come here and he's discussing floating point arithmetic. Okay, so here the discussion is centered around Dojo. So Dojo is nothing but a standard which Tesla has released for their floating point arithmetic. Okay, for training their ADAS system. Okay, so they use machine learning there, and they have two approaches. One is training, another is inference. So training is done on some custom computer which was designed by Tesla themselves. They don't use any other Apple or some other computer. They do it by their own. Okay, so here he was discussing that that for Dojo they are betting on FP16. Okay, the format which I discussed, it is called half precision, and is so that it feels FP32 and existing software just works. We considered FP8 for a while. Okay, that is what he says. He considered using FP8, floating point 8, but everyone hated it. Okay, that means they didn't get some desired outcome using that. Okay, he has even taken a poll about that on Twitter. And for inference, which is the second step of any ML algorithm, int 8 works great. Okay, so there's a rule of thumb that if you want to do training, do it on a floating point processor. That's why GPUs are getting popular day by day. And for inference, use integer arithmetic. Okay, or the computers which are specialized in integer arithmetic like FPGAs. That is where Xilinx FPGAs come into play, and people are actually crazy about throwing their inference logic on Xilinx or any FPGA for that matter. Okay, so here onwards I discuss a few cutting edge research papers. Okay, I'll just give you a brief overview of what these research papers are actually trying to discuss, and I want you to actually go and spend your time here and understand for yourself that how beautiful people are actually coming up with these new ideas. Okay, now in this paper, which was a NeurIPS 2018 entry, okay, it was selected for NeurIPS 2018. It's a popular conference for people who are interested in machine learning. Okay, so training deep neural networks with 8-bit floating point numbers. So see here, they start off by saying that the state-of-art hardware platforms for training deep neural networks are moving from traditional single precision, which is the 32-bit computations, towards 16 bits of precision. So what do they achieve after that? Is that they see that the throughput is improved by at least 2 to 4 times. Okay, so that's quite a big deal. And the same folks, okay, these folks are actually very actively researching on this topic at the IBM TJ Watson Research Center. Recently, they have even they've also authored a paper which says that training deep neural networks with 4 bits of floating point numbers. Okay, so that's again an interesting read. I want you to, I wish, I encourage you to take a look at all these papers. And now moving ahead, this is a very again interesting paper which was given by Facebook or Meta AI Research. There's this person called Jeff Johnson. He's a one-man army who is leading that particular research in Facebook. And what he did was basically, let me give you a brief overview. Imagine now, just like logarithms, right? Logarithms were invented in order to handle the scientific notation numbers very easily, right? So what happens when you use logarithmic number system? This is what this guy has explored here. Similar to what when you use when you try to convert the floating point arithmetic into using some logarithmic number system, multiplication translates into addition, right? Remember that log of a into b is equal to log of a plus log of b. and division translates into subtraction. So that is where the main pain points get resolved, and this fellow claims that okay, they have achieved some good numbers. Okay, that is the gist of his research. I won't go in depth of that, but I encourage you to take a look at this paper. Okay, so he ends up saving quite a lot of silicon footprint as well as some power, and he has actually drafted this design on an ASIC. So that's quite an interesting approach. So that's a good thing. So this fellow is actually he's a prolific researcher. He's sending out very quality research, and I feel highly respect, or I have nothing but awe for this fellow who is single-handedly taking up the research at Facebook. Okay, I want to meet him someday. Okay, and see what is he eating, how is he surviving anyway. Okay, so next thing is next a paper by Xilinx themselves. Okay, my own company, where my employer. So there they discuss that okay, they have achieved a very high performance neural network. Okay, higher performance neural network with small floating point. Now what is small floating point? So it is nothing but a small floating point, call it as floating point with very small bit widths of 8, 16 and so on. I mean very small, not as high as 32 but smaller than 16 at least. Okay, so they have used a 7-bit small floating point number, and what have they shown here is that they achieved similar performance with higher compute throughput. Okay, they didn't end up degrading the accuracy of that neural network, but rather preserving the accuracy. They annotate the shared content. Okay, Abhishek Dikshit, do you want to? Okay, I'll decline.
No, sir, it happened by mistake.
Okay, no worries. Okay, so yeah, so I was saying that it is, they end up showing a very, I mean they show a 60% increase in the performance while keeping the accuracy same. Okay, so quite an interesting read. And now finally coming back to Dojo. So Dojo, they there's this what I would say is Elon Musk and his team, they actually ended up making or exploiting this floating point arithmetic for their benefit. They have exploited it such that they actually made the mantissa and the exponent and even the bias field reconfigurable. Okay, so unlike the traditional computers, which let me show you the floating point annotation. So these are all fixed for traditional compute. So this is all fixed to 11, 52 and then 5 and 10. But this fellow, they actually made it all programmable, so that now you can actually train it for those particular standard. So they ended up making the floating point standard a reconfigurable one. Okay, so as a result, they saved a lot of power, which is gone in when you train a particular neural network, and they achieved a very fast convergence. Okay, so now last thing is the fun application, which is the Quake 3 fast inverse square root algorithm. So this has actually motivated me to, this has been foundational for me to invent my first algorithm, which I have mentioned. This has been given, this is in, currently under scrutiny at the Xilinx patent committee. Okay, the first thing is, if you see, this is the floating point equation which I just told you in the previous slide. And let's say if you take binary log of that, so assume that, so what we intend to do here first is, given a number x, which is obviously in floating point, you want to find the inverse square root of that. Okay, how does the computer do? So computer does it using Taylor series approximation, but there happened to be this interesting person who actually approximated it without using a complex approach of Taylor series. Okay, let's see how he did that. Okay, so assume that because we are taking inverse square root, we assume that the numbers that are coming are always positive. Hence, we are ignoring this. Okay, and what we have is only this. So if I take binary logarithm of that, now I have motivated here, I put here in brackets that why did I take binary logarithm? So understand that I see twos, I can see twos all around here. Okay, that is the reason I take binary logarithm, just in order to remove this 2, because log 2 of 2 is nothing but 1. Okay, just in order to save some complexity of compute. Okay, I think it's already 5. I'll try to wrap it up. Okay, so if I take binary logarithm, what happens is this, that I end up approximating it as bit representation of x divided by 2 raised to m plus mu minus b, where mu is a pre-computed constant. Okay, so fundamental approximation here is binary logarithm of x. I mean, binary logarithm of 1 plus x is approximately equal to x plus mu, where x is, where mu is a predefined constant. So it is generally taken to be 0.05 or something. Okay, and if you see, this number is always less than 1. Okay, because it is 2 raised to m. So that has been fundamental approach here. And what I have here is, this is bx, which is the binary bit representation of this floating point number. Let me show you a quick example. I won't take much time. I had this here, but somehow I forgot. Okay, let us try it here. Okay, allow. Okay, so this is a website which helps you understand the floating point number. Let's say I want to store 3.14162, the pi value. Okay, what I have here, this is how it is actually stored. So the numbers which are ticked are the only, those are 1 in that binary format, rest all are 0. Okay, so this is how it is stored. If you see sign bit is 0, which means it's a positive number. If I do negative pi, this becomes 1. Okay, so what I mean here is, this is the bit representation. So this is how the bit is, and if I were to read it as an integer number, this is how it will be represented in hex. Okay, so this hex number, this is bx. Okay, I hope you understand. This is nothing but bx, which is the bit representation of input x. Okay, x is the input floating point number. Now what did this fellow say? They said that, okay, binary log of x is approximately equal to bit representation of number divided by 2 raised to m. Now this division by 2 is achieved by using right shift, okay, in computers. So it's very easy and compute friendly, and this simple integer addition, it requires nothing. So but I want to compute inverse square root. So if I were to do some more mathematics, what I have here is this: if y is equal to 1 over square root of x, then bit representation of y in floating point is approximately equal to bit representation of x divided by 2 and negative of that plus some constant. Okay, plus some constant. So it's very easy application, very easy to implement in computers, and it requires only one adder, that's all, and one multiplier here, that's all. Or even if you store this constant as a hard-coded number, what you require, or the highest complexity circuit here, is addition, because here, but if you again divide it by 2, it is nothing but right shift. So a code, a corresponding C code can be written like this. So a number is given inside float, it is taken to be as float, and then see here, there is this evil bit level hacking. Okay, they store, although they store it as a floating point number, but they extract the bits out of it, which is nothing but this number. Okay, this number, hexadecimal representation. If you
Purvish, sorry for the
yes,
interruption. This is which
sorry.
app or software you are using?
No, this is
This.
website. This is website. The,
Acha.
I have linked here. I have linked it there.
Hmm.
Okay, you
Okay.
can see. Yeah. At the end, I'll also present the QR code to access this PPT. So you can see.
Okay.
Okay. There's no software. This is just an online web page. That's all.
Acha. Okay.
Okay, yes. Okay. Just a couple of more minutes, just 1 minute or so, and then I'll be done. Okay. So once you extract the bit widths, as per this equation, I want to just divide it by 2, take the negative and add to it. So this constant is stored in this way, which is called the magic number. I divide it by 2, that means I right shift by 1, and then I subtract it and I add this to this number. And then again I read it as though it was a float. Okay, now there are some more piece of code here, which is nothing but a Newton-Raphson iteration method in order to approximate 1 over square root of x. Okay, this is a basic calculus class, if you remember. Simple thing. Okay, there is nothing more compute circuitry involved here. Imagine Taylor series and imagine this. It's very easy to do. Very intelligent algorithm. Okay, I thoroughly request you all to take a look at this algorithm. There's this interesting YouTube video which is explaining the same. I've linked here. You can take a look by clicking on this link. Okay. Now, yeah, so interesting reads. So I motivate you to take a look at the IEEE 754 floating point standard paper. It is available. And then this book I mentioned, you can find it in your library, or there's even ebook that is available. And then there's this fourth, which is engineering mathematics with MATLAB. I don't recommend use of MATLAB, but I like the way this author has written it. And then there's this paper which I mentioned earlier, primes is in P. Very interesting paper. And then there's this small ebook called Computers as Crucible, right? I would highly recommend people who have their strong background in mathematics and compute to take a look at that. And then lastly, if you are all interested in if someone is interested in taking a look at how to exploit FPGAs for this particular application, I would recommend you to take this look at the 7th reference, which is Parallel Programming for FPGAs. It's a free ebook which is available, and it is given by Xilinx open source. I hope this helps. Okay, so by this I end this talk, and you can access this presentation by scanning this QR code. You might want to take a screenshot of your screen currently. Okay, so you can access this presentation by scanning this QR code. And earlier I recorded the same lecture, although the topic was same, but the lecture was not the same. Okay, which I delivered at the COEP Ramanujan Club. Okay, I have put it freely available on YouTube. I hope it helps, and you can get in touch with me here, which is deltaneighbor@gmail.com. I'm just in your Delta neighborhood. Thanks a lot.
Okay. Thank you. Thank you, Urvish. So
Yes.
if merely just we take the picture of the slide, can we access it?
Yes,
or
absolutely.
it will need a PDF by JPG?
No. So if you just scan this, it will actually take you to the PDF.
Acha, so JPG also will work. Okay.
Yes.
Okay. Thank you, Urvish.
Thanks a lot.
So I thank Urvish from bottom of my heart for taking time from your busy schedule to be a guest speaker at NDLI platform. Yes. Hello. I request participants to mute from your side. Now this session is open for question and answers if anybody is having. Anybody have a question? Yes? Someone is speaking. I can face the noise. No questions? I again request participants from their side.
Open होई ना chat box. Yeah.
Just a minute. Yeah.
Yes, yes.
Yes. So I enjoyed basically 2-3 topics from your talk, Urvish.
Thank you.
So
Thank you.
data path implementation, control path and compute path. These are the two types of paths that
Correct.
I can understand. And the concepts of floating point and fixed point that we can differentiate, at least from mathematical
Yes.
point of view, I can understand those things.
Correct.
There is one question
Yes.
from participants
Uh,
that what is the scope of computer arithmetic by placement point of view?
Please. Oh,
it's a it's a very good question.
it's a nice one. Okay.
Yeah.
So let me give you a very quick understanding. If you plan to understand, I mean, it depends which companies you are trying to apply for. Companies like TCS and other who just want to get their job done, they don't want you to understand computer arithmetic. So it's fairly useless topic for that. But if you were to apply for some companies who are, the creamy layer as we call it, be it Xilinx um, or even Amazon or Apple or Microsoft, they tend to ask you or they want you to understand that, okay, how much in-depth knowledge you have. So I covered programming, right? So in case if you are to run that particular code, if you just use float and double format, and if you run that code and if you use custom precision for each and every data type, I bet you not only be able to get the code output, but you will be able to get it in you'll be able to do it in faster time. Okay, so it is when then this matters that you need to understand about computer arithmetic.
Okay. Thank you. So he was a student from Division 7, first year
Okay,
student from
okay,
COEP. So they
okay.
are worried about their placements after
Placements in the
4
first year.
years. Yes, in first year only. So they are motivated with respect to placement. Yes.
Okay, okay, no
And
worries.
secondly, I enjoyed that conversation regarding dojo in between Carmack and Musk. So
Musk,
that
yes,
was very nice conversation that actually you had it in that subject PDF also.
correct.
I was trying to read it, but today
It
I saw
is
it on the slide. Yeah. So
okay.
your presence and wise words helped us a lot to
Thanks a lot.
magnify our cause in best possible way. So I thank once again on behalf of COEP, NDLI to your enlightening words that inspired so many people out there. Okay.
Thanks a lot.
Yeah.
One
Yeah.
one last note I would like to say that
Yes.
to the
Yes.
interesting question that audience has posed. Um, I think don't study for
For
aspects.
placements.
Never. I never studied for placements. Okay, here am I working at my dream company. Okay. I never studied for placements. In fact, I failed at placements. Okay.
Hmm.
To quench your thirst of knowledge. That's all.
His next question is how can we use the approach in programming? How we can use this approach, computer arithmetic in programming? Basically, it's dependent on programming all the time. No?
Correct.
Everything that abscissa, mantissa, all those things, these language computer can understand it. So that is used in programming.
Correct.
So
No,
your answer.
so my thing is, see, if you want to, whenever you try to do a program, understand that what is the data you're trying to process. Okay, and how
Huh.
you want to do it. So once you get an understanding, as I already told you, that if the data is coming in a quantized format from a ADC, or if a data is the dynamic range is quite constant, okay, then you can safely go about using integer data type for that. Okay, with the integer data type having the same dynamic range as the input data. Okay, so that would not only accelerate your compute, but even it will help your computer to save some lot of silicon time, and even compute overhead will be reduced.
He's asking, can we enhance the quality of code
Yes, yes,
using? Huh,
absolutely.
so how to write a better quality code
How to
using these concepts?
Yeah, no, I just told, right? If and first you have to analyze that what input data you are processing, and depending on that, you need to discuss. What do I mean by analysis? you analyze the dynamic range that is required to represent those particular set of numbers. And once you feel that, okay, I have these many numbers and these are the possible sets that I need to play with, you can easily just go about using particular standard rather than float.
Yes.
So let me give you one quick demo. So because if you have seen that this double is 64-bit precision, so double is still slower, or in very if computers are actually optimized for double precision format. So I mean either will be slower on a 64-bit computer. Okay, so it depends on what computer you want to target. Let's say if you are using FPGAs, so FPGAs get their data from ADCs, so there no need to use any floating point numbers at all. In case I say so much, if you are using FPGAs, no need to use floating point arithmetic at all.
Yeah. Okay, you got it, Atharva? Yes. Yes, he got it. He's saying thanks. Next
Okay.
question is from Bharati Chandra.
Okay.
How can we link data analysis with a computer arithmetic?
How can we link data analysis? It's quite vague. I mean,
Data analysis is a statistical branch. Actually, it has in some relation, it is related with, actually, it covers 5 branches.
okay.
Computer science, statistics, mathematics, and software part like R and Python. So that collectively is called as a data analysis. So if you have
Oh.
a data, if you have a data of anything, say for example, suppose I'm having a class of 70 students and I'm going to measure their height. That is what is numerical data that is available to me. Now, how to analyze this data means what is central tendency of this mean, variance, standard deviation. So that is what is called as data analysis, and in larger extent, we can make use of softwares. And when software comes, the programming part comes.
Yes.
And just now, you can interlink with the subject of computer arithmetic. You can enhance the coding in R using computer arithmetic,
Oh,
whatever it is.
that's I got it.
Like
I
that,
got
we
it.
can link it. This is what I feel. This is what my perception. So you can.
Yeah. So as per your perception, if I were to go about, say, let's say all students in first year, if you want to analyze heights, okay, you go about taking height. Now, nobody will be lesser than 1 meter, right? So then dynamic range is fixed.
That
So
probability is 0. Yeah.
probability is 0. So
Yes.
then you need to say that, okay, now my number will be greater than 1. So maybe 1.73 something. Okay, then you say that, okay, because it is greater than 1, you say that, okay, you use fixed point numbers, right? And the amount of precision you required, you say that, okay, even with this data, I'll be able to do that. So even 8-bit numbers would be very convenient. Let's say if you have dynamic in a very closer area, or the distribution is very close, then take the binary logarithm of the highest data point which is there and call it that bit value. Right. If 256 is the highest number you have, take binary logarithm of that, you will get 8. That means int 8 would be sufficient enough for that. And for if you want to keep it still safe, make it int 32 or something, which is there standard, or even int 16 would work.
Yes.
So that would
Yeah.
help you under or design your program in a good way, or the actual way it is, but it will also help you speed up your computation and relieve your computer for some other good task.
Yes. Any other question from audience?
So
You.
there's one project topic which I would like to give you people, is to find whether given very big number, which is like 50-60 digits integer number, how to find whether that is prime. Then you will appreciate that this computer arithmetic topic. Okay.
So unless you do some practical things,
Correct.
you will not understand the strength of this subject.
Correct, correct. So try, the problem statement is simple. Input is a 50-60 digit integer number, and you have to find it whether it is prime or not. Go about doing it.
So you have to write a code.
Yes.
So any 50-60 digit number I will enter, I will feed.
Yes. Yes.
And you should get the answer as outcome, whether it is a prime or not a prime.
Yes.
Okay, so you got it, students? Very nice. So I hope some of you will try out this problem as a project. So please repeat the question. There is a request. Okay, so you have to enter a 50 or 60 digit number to your device, whatever software you are using, and you have to write a code to test whether this number is a prime number or not a prime number. You got it, Bhavin? Yeah, thank you. Yes. So Spandan is saying that thank you, sir. Very nice session. Okay.
Thanks a lot.
Yes.
Much appreciated.
Yes, really we have enjoyed. I can see from the chat box we have enjoyed this session. Lastly, I would like to thank the organizing committee of COEP, Dr. Bibi Ahuja, Director Sir, Dr. Vibha Vyas Madam, Library Chairman, Dr. Pratibha Wankhede Madam, Librarian, and Anita Madam. She was helping me a lot from last 3-4 days. She was entertaining me from every other side to arrange this session. She made that flair. So actually, I'm thankful to this organizing committee, to COEP, to all higher authorities who are involved in this session while arranging this session. So Parth is also saying that it was an amazing session. Bhavin is saying that great session. So actually, there is a great person in front of us. I already introduced him. He's having lots of faces. We cannot count it, uncountable. So you know what is meant by countable and uncountable set from mathematical point of view. The first year students, I hope they can understand what I'm saying. Okay, so shall we stop? Shall we end up the meeting? Before I end up, I have to make one important announcement. Listen to me carefully. This session will be freezed by me, and it will take a time. It will take tomorrow because the number of participants is large. We have to tick mark each and everyone's attendance over there one by one. So it will take time for me to freeze this session on NDLI. After that, you will get the certificate. So be patient. Don't be impatient. And in today's session, Urvish said that you should not think from the placement point of view. But Urvish, I will say you, my experience is that these students are asking me for certificates. Ma'am, I will attend the session, will I get a certificate? So you can relate it with the placement and getting certificates, what's their thinking is about. So you should not attend sessions to get the certificate, it's for the gain of knowledge. You should gain a knowledge. Now that's a bigger thing than that certificate, than that piece of paper. Of course, certificate matters a lot, I can understand. But from last 2-3 days, I'm observing this. Okay, so definitely for this session, you are going to get a certificate. Till then, you have to be patient till tomorrow. I will be freezing this session. And then day after tomorrow, you start asking me. I can say like that. So with this note, shall we stop? Sure. One more thing. How to mark attendance. You are not going to mark the attendance. I am going to mark your attendance. Okay? It was a great session. Yes. Those who are having lecture, they can leave the meeting. Thank you. Yeah. No, thank you, Urvish. Yeah. Yes.
For those who are collecting certificates, it's like try to relate it with honeybees. They try collecting the honey, and at the end they are not getting it. Okay, it gets destroyed. Yeah. Man takes it away. Yes. Okay. So always try to be, take the mark which is the Shreya ka marg as per Upanishads, and always indulge in something higher than just these finite certificates or some attendance. Yes. Okay. Thank you all of you again. Thanks a lot. I'm loving this meeting. Yeah. Thanks a lot, man. Bye. Thank you.